Hey, so welcome back to more LeetCode problems. So today what we're going to do is continue on with this Blind75 list. So if you don't know what it is, it's essentially a popular list of algorithm practice problems or LeetCode problems that was designed by some FANG engineers to really help solidify which problems you should be practicing and also organize them by different algorithms as well as different data structures that you often deal with. So all of these kind of focus on the different patterns that you might see when you do these questions, so that rather than you're just aimlessly picking questions from a list, you're actually focusing on a particular problem type and getting good at that category, rather than just going through a LeetCode question, failing and trying again, and just keep iterating over that over just some random list of questions. This is like a curated, super popular list of problems. So we'll go ahead and we'll do these tree problems here. There's 11 of them, so it's going to be a long episode, but I'll go through for each one the algorithm and the implementation of it just step by step. So let's get to it. So this invert binary tree one, essentially what you're given here is a binary tree, and we want to invert it. And all that means is essentially everything on the left will now be on the right, and that kind of just recursively goes down here. And so like this becomes the right and this becomes the left. This used to be left and now it's on the right. This is the left now. This one's now, instead of it being on the left, it will be on the right, and so forth, right? So it all gets kind of swapped here. All right, and so essentially if we look at this first one, we have 4, and that root kind of remains the same. They never change, but you can see 2, which used to be on the left, it's now on the right. Same thing with 7, they swap places. But then also 9 doesn't go here. The really kind of trick here is that 9 is now actually on the left of the left-hand subtree here. And so it's actually like all the way over here now. All right, so it doesn't just switch with its like kind of neighboring like sister node. It actually swaps with what you call the cousin node, which is essentially a node in the separate subtree, but on the same kind of level here. All right, and so essentially what we're going to do is just, honestly, it's quite simple. You just recursively swap the left and the right nodes, and you just keep doing that until you hit your base case, and you just return that kind of switching of the nodes up the tree. All right, so typically I'll go through a lot of drawing here, but I think the code is pretty self-explanatory. So I'll just quickly show it to you and we'll review it. So essentially the base case is just, okay, if there's no root, we're just going to return nothing. And that's just okay. Say if we're giving like nothing at all and there's no tree, let's just return none. This also works where, okay, when we hit this base case here and we want to swap like its left child with something, well, this is null. And so when we swap this, say over here, this position, we also want this to be none here, right? And so we would want to return a none whenever we hit a kind of leaf node or the bottommost of this tree. All right, and so from here, we're expecting to return some root. But before we do that, we want to swap each left node as the right node and each right node as the left node. And so to do that, essentially, typically when you're doing swaps, you can think of this as variables. You need kind of a temporary node to hold like the, let's just call it the temporary value of it before you swap it, just because when you're switching nodes, you kind of have to have a temporary variable. And so this pattern is typically, well, let's just store the value of what we're going to be swapping for the new left node. And so the left node is going to become basically the inversion by calling the right node. And so this will be basically the temp left. But for now, we can now update this right node as basically the same thing here, but we're now swapping with the left. And so the reason why we had to store this in the temporary variable here is because we're passing it here, and well, we don't want to use this result from this method call. So now we can basically set the left as the temp left, and that's the end of this algorithm. So let's run it. Oh, unexpected indent. That's just because for some reason there was an extra space here. Looks good. And success. So that's the first one there. Let's go ahead and move on to the next one. So this one's called maximum depth of a binary tree. So essentially all that we're going to do here is we want to find, okay, what is the total depth of this tree, or really the total height? And that's going to be 3 in this case. So it's kind of like 3 nodes high on the longest kind of path here. So to do this, all that you have to use is what's called breadth first search, and I'm already expecting that you kind of know what this is. So it's essentially like level order traversal. You just traverse one level at a time. So we'll visit this one, then this one, then this one, and then this one, and then this one. And so basically we're just going to travel a whole level and then say, okay, this has a depth of 1. This one has a depth of 2. This one has a depth of 3. And once we hit this base case, and we see that, okay, there's nothing left here, we just return 3. Okay, so to do this, you can do it 2 different ways, one recursively and one iteratively. Both are good, but typically what people say is that the iterative way is better because you don't have to worry about the application stack, like hitting like a memory issue. And so typically iteratively is better. And so to do this, a lot of it is blueprint code. So typically when you want to write breadth first search recursively, this is how you do it. So I'll just write out the blueprint code. And so we want to return here though, some level. Okay, so we'll say like the current level, or really I guess the max level, if you want to call it that, or max depth. And so initially this max depth will just be 0. And we want to say, okay, how do we traverse this in a breadth first search manner? And so to do this, the code that you write is that, okay, well, we have to have a queue because that's how depth first search works. And so we're going to implicitly or explicitly, define this. So we'll set our queue equal to the double-ended queue in Python, and we'll just set our root in that queue. And we just say, okay, while we have something on this queue, we're going to traverse basically everything that's in this queue. And so what this actually symbolizes here is we're going to iterate through every node in the current level. And so basically every single time you iterate through your entire queue and what's on it, you're basically just iterating through the entire level. So what that looks like is basically at first, we're going to iterate through this level 0, then we'll iterate through the entire of level 1, and then we'll iterate through the entire of level 2. Okay, so that's what's going to be happening within this for loop here. And so all that you want to do is you want to add to the queue the nodes that will come after this level. And so to do that, we just say, okay, if node.left, or sorry, we first have to get our node, and so we just pull it off our queue. So the queue.pop left. And so if we have a left node, then let's add it to our queue. So queue.append node.left. We're basically just repeating this for our right node. And so this is how you essentially just traverse it in a breadth first search manner. But how do we actually get the maximum depth? Well, with each iteration, after we fully explored essentially this entire level, we've just said, okay, we've just explored an entire level here, so we can now increment our max depth by 1 here. So I believe that looks good. Oh, we got an error, so we have a none type. So all that we have to do is say, okay, if we don't have a node here, we just want to return 0. So let's return a 0 in this case. Looks good, and let's move on to the next problem here. So this one's called same tree. And so all that you have to do here is say, okay, we're given 2 trees. Are they the same thing? So do they have the exact same values at every single placement? Otherwise, if they aren't exactly identical, we want to return false. Okay, so essentially all that we're going to do is we can traverse this in any possible manner, whether you want to use preorder, inorder, any type of depth first search, or you can do breadth first search, whatever way you want. But as you iterate in that traversal, you always want to check, okay, is the current node the same as the current node on the other tree? If not, let's return false. And so to do this, I find using a depth first search is the easiest to write. So we'll just write a recursive solution using depth first search, and we're just basically iterating through it using depth first search. And at each node, we're just going to say, okay, are these the same node? All right, so to do this, all you have to say is, okay, what if they're both null? That's kind of the base case here. So if they're both null, they're the same. All right, and so we also want to turn true in that case because, well, when you're checking kind of these leaf nodes, you want to make sure that they're both null. And if they are, then that's true. That is identical. in that case. So, okay, if P, or basically if this is null and the Q node is null, that is valid, so we return true. Otherwise, if one of them's null and the other one isn't, we want to return false because they don't match. They're non-identical. And so if either of these are not null, but one of them is, then we want to return false here. Otherwise, we just want to keep recursively calling this algorithm until we see that, okay, they're all the same or they're all not the same. And so we're essentially just returning, okay, are these values the same? And does this hold true when we traverse this entire tree? And so what that looks like is essentially, okay, we're just going to keep calling our method here until this isn't no longer valid and we'll return false. So we just want to go left in both trees and we want to go right in both trees. And that's essentially it. So let's try running that. Looks good. And success. So that's another implementation. And now that's 4 problems down. Let's do the medium problem. So there's 5 medium problems here. So let's do the next one called longest common ancestor of a binary search tree. And so this is actually a very common problem. A lot of problems kind of extend. They call it the LCA, lowest common ancestor. So this is kind of the base entry of that problem type. And so essentially all that you want to do is you're given 2 nodes, or 2 values, I guess. No, it's 2 nodes. And you want to find them. So in this case, we want to find 2 and 8. So those are these. And so what the lowest common ancestor is essentially like an ancestor is a node that came before a particular node. And so an ancestor of 8 is 6, while an ancestor of 5 would be 4, 2, or 6. Any node that's like above it, essentially, and can get to it. So something like 0 wouldn't be like an ancestor of 5 here. Okay, so it has to be like within that path from the root. All right, and so to do this, essentially what we're just going to keep track of is 2 things here. One of them is that, okay, are both nodes in this subtree? And so we want to say, okay, say if we're at 6 here, we want to see, okay, can we reach both of these nodes from this node here? And that's true because 2 and 8 lie underneath it. And so this would be valid. But in the case where that, okay, what about this one where P is 2 and 4, which are, I think, these? One catch here is that the lowest common ancestor can be one of these nodes. And so we see that, okay, from 6, can we reach 2 and 4? Yes, we can. And so we basically traverse down the left subtree because we know it's not down the right subtree. And then we're at 2. And we say, okay, can we reach 2 and 4 from 2? Yes, we can. And so we basically say, okay, well, what about can we go any lower? Because we want the lowest one. And well, that's not true because if we go down all the way to 4, you can't reach 2 anymore. You can only reach 4. And so that doesn't work. So the lowest one was actually 2. All right, so I hope this explanation helped a little bit. I'll go through the implementation and we'll just chat while we implement it. So we're going to split this into 2 different thoughts here. So the first one is, okay, are they in this subtree? Are they this node or lower? And so essentially we just want to say, okay, contains both. We'll just call the method that, and we'll just say, okay, well, we want the current root node as well as P and Q here. And to see that, okay, do we have all these nodes? We just want to see, okay, I think, do we do, oh no, it's not this one. Okay, so one of these you want to actually copy paste one of the previous implementations, but I believe that's a different one. But essentially we're just going to say, okay, well, we want to find 2 things. And so if the root is null, let's just say we found 0 things here. So if the root is null, we weren't able to find either of these. And that's also the base case of we're going to search down this tree. And once we hit kind of the leaf here and below it, we want to start at 0, and basically as we iterate up this tree and find them, we'll be kind of adding 1 and then adding 1 again whenever we find these nodes, okay? And so from here we just say, well, how do we actually increment this value whenever we find these nodes? And basically we're just saying, okay, if the value is either P or Q, then let's increment this result by 1. And so to do that, we just say, okay, if this is in P.val or Q.val, so if this is in kind of this tuple here, then we know that this subtree or this ancestor's subtree contains one of these nodes. And so we just want to do this for all left and right possible options beneath this node. So return this plus, and basically we're just recursively calling this for both the left and the right subtrees. And so we just say root.left, p, q, and we add with the right subtree. Great, and so from here, we want to actually perform the implementation where we actually traverse all these possible paths and figure out what is this lowest common ancestor. And so to do this, let me just think for a moment. In this case, so we have the LCA here, and we have this method where we containerize how we can tell if the current node contains them. However, if we find one at a lower level, we want to use that instead. And so although 6 works, if we can use 2, that's much better because it's lower. And so to do this, we basically say, okay, well, if we have a left path, or if root, and the left node contains them both, so self dot contains both. We see that, okay, this left node contains both P and Q in it, then let's use this result. And so that's just going to be, okay, let's return root.left.val. And so if the left node contains them both, we'll return that instead of the root node. Otherwise, if one in the right subtree, so one that's lower to it, one of the children on the right subtree contain it, we'll use that one instead. And so we'll basically return root.right.val. Otherwise, we'll just return a root here. Let's try running that. Oh, has no index because it's an integer. Let's just think here. So this is saying root.right.val. Root.right. Root.left. Let's try that. Looks good. Oh, looks like we hit an edge case here. Let's just take a peek at this edge case. So what does this look like? So can I view it? Don't believe so. Typically, often you can visualize them. Not sure how here. But we run this. What are we expecting? So we're outputting 2, but we can get to 4. Let's just see, we'll return left, otherwise we return right, otherwise we return root. We're saying contains both left and right. And if the root.val is in there, oh, I see, sorry. So we don't want to just stop there. We want to go as low as we possibly can in the left and right subtree. And so we're just going to be recursively calling this whenever we return it. So we'll see, okay, if the left subtree contains these 2 nodes here, P and Q, then let's try to find a lowest common ancestor within that subtree, and we would recursively do that. So we want to go within that subtree, but as low as possible. So to do that, we just say self.lowest common ancestor, and then we just say root.left, comma, P and Q. All right, and so we do this exact same thing, but for the right side. Let's try that. Looks good. And success. So that's another one down. So let's go ahead and do the binary tree level order traversal. And so this essentially, we're just going to implement breadth first search. So we just want to output basically a two-dimensional array or a list of lists where we're just basically outputting a list for every single level. So the first level contains 3, the second level contains 9 and 20, and so forth. So we're basically just creating a separate list for every single level. And so we're basically just doing the exact same thing that we did for the maximum depth of binary tree. If we look at this, where we're essentially just using this algorithm, using breadth first search, but just tweaking it so that we just output each individual level rather than just what's the height of the tree. All right, so to do this, we just say, okay, let's implement our templated breadth first search code here. So we need a queue, and so that uses a double-ended queue here. We put the root on it, and so while we have something on our queue, let's iterate through that entire level. So in the range of the length of our queue here, so iterate through one level. And so basically to continuously do this in a breadth first search manner, we just want to add the left and the right nodes. So we just want to pop off whatever is in our queue. And we just say, okay, well, oh, I see that we have some, weight space issues. So if there's a left node, let's add that to our queue. And we also want to add whatever is on the right of our queue. So from here, we just want to say, okay, this is how we kind of traverse this in a level order traversal. But from here, how do we actually output and get this kind of two-dimensional array? So let's create that array here, and we'll call it response. And so essentially, this code here represents one entire level. And so after we visited that level, we'll basically add that level to our array here. And so we'll basically append it. So that looks like this. Let's append that level. And so that level will then be basically an empty array at first. And so as we pop off each node in our level, we'll just basically add them to that array. So level.append this root. And I believe we just want their values. And so we just copy their values here. Oh, and I just have a syntax issue. And here, so this is a none type. So let me just think. So I think the only edge case here is okay. If the root is null, naturally, we're just going to want to return an empty array. And success, so that's another one down. So let's keep going here. So we've done 6 so far, and we just have 5 more to go. And so this one's called validate binary search tree. And so all this is if you know what a binary search tree or BST is, essentially what that means is if you ran in order traversal, you would expect to kind of read them in sorted order. And so binary search tree just enables you to perform kind of an in order traversal to read them like in a sorted order. And so what that will look like is in order to confirm that we're meeting the criteria of a binary search tree, we want to define that criteria. And so what that will look like is, okay, well, you want to be able to kind of read this from left to right in sorted order. So it goes 1, 2, then 3, or this one, so it goes 1, but we see, oh, it goes 5, so 1, 5, and then it goes like 3, 4, 6, and we can see that that doesn't work here. All right, so they should be increasing as we look from left to right here, but that doesn't work. And so that we know, okay, well, what's faulty here? Well, we know that, well, the node value is 5, but its right child is 4, right? So that looks like this. So this should be more like something like 2, and then it goes to 4 and 3 and 6, right? And so this node here, 5, should always be kind of less than what comes after it. Same thing here where, okay, what if this was 4 here, and then this one was 5? Well, this also doesn't work because we have this issue here where 3 is technically on the right side of 4, but 3 is smaller than 4, and so that also is an invalid case. All right, so what we're going to do is essentially we're going to look at this in a breadth first search manner, and we're just going to keep track of what was the previous thing that we saw, and kind of like what's like the previous thing that we saw is always going to be like the current max thing we've seen so far. Because if you're reading it in increasing order, the last thing you saw is always going to be the biggest thing you've seen so far because it's always increasing. And so we just say, okay, if the last thing we saw so far is actually bigger than the current thing we're looking at, then naturally like it's not increasing because we should always be seeing the new biggest thing. So if that doesn't make much sense, I think I'll write the code and that will help a lot. All right, so essentially we want to see, okay, what is the previous biggest thing we saw so far? Initially we'll just say that's negative infinity, the smallest number we have. And so we'll return true if we never found a reason to say that it's not in sorted order or in BST. And so to do this, we'll just say, we'll look at this through a depth first search manner. And so I'll write out the blueprint code for depth first search. And so this uses a stack, while breadth first search we used earlier uses a queue. So while we have basically something on our stack or we have a root node, and so typically the code just looks like this here, where we're just recursively appending to our stack the current root node, and then we set the current root node to the left node, and you just kind of keep going left until you hit the edge case or the bottom node. And so from here you just want to say, okay, let's kind of pop off our node from our stack. And so this will give us kind of what's at the bottom, because it keeps going left, 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 left. So it keeps going left until it hits nothing here. And we'll basically have a stack that looks like 5 and then 1. And so we'll basically be popping up 1 off the stack. All right, and so this is kind of what we typically want to do here. So perform something happens at this point. This is just kind of populating what's on the stack. So after you do something, then you just go down the right path if you can. All right, and so from here, what do we want to do again? We want to make sure that it's in sorted order. And so essentially, all that we have to do is say, okay, if the root node is not actually bigger than the previous biggest thing we've seen so far, let's return false, because that is invalid. And so the only thing that's left to do is how do we keep this updated? Well, the previous node is always going to be basically the current node that we just looked at. And so that's going to be previous set to root, and then root will be set to whatever is right of it. Okay, and so if we don't hit this condition, we return true at the end of it. So let's try running that. What's wrong here? So, because this is a node, well, this is a value. So we just do root.val. Let's just see what's wrong here between tree node and int. So I thought I did root.val. What's previous? So we just want to do root.val here as well. Looks good. And success. So that's another one down. So that's how we validate it. And so now we're just doing the last 4 ones here, and I would say these are kind of the harder ones. Actually, this one's not so bad, but these 3 ones are the hard ones, so you want to stick around for those. But for this, it kind of reminds me of a min heap or a heap problem. And so essentially what we're going to do is we want to find the kth smallest element. And so all that we have to do is basically we'll do this in, I think it's preorder. Yeah, so we use preorder. And so what that means is basically if we're dealing with a binary search tree, which we are, that means that, okay, if we use preorder traversal, we should be looking at this, actually we'll be looking at this in order, I believe. Yeah, in order. And so if we use like in order traversal, then we're basically looking at it in increasing order. No, we want preorder, sorry. In order means you look at the current node, the next node. We want preorder because we're always going to go as left as we can until we hit the leftmost node and we kind of recurse upward. So we'll use preorder traversal, and we want to be looking at it basically if this was an array, and so we're going to look at the smallest value, then the next smallest, and then so forth. And so if we want the kth smallest element, we basically just have to iterate through this list or this tree k times, right? And so if it goes 1, 2, 3, 4, we'll basically use preorder traversal to iterate in this direction. And so then, okay, if k is equal to 2, we want basically the second smallest node, and so that will be this one here. And so we'll iterate once and then twice, and then we'll return whatever node is there. All right, and so to implement this, we basically once again want to use a depth first search manner, or really preorder, I believe. Yeah, and so essentially we'll just be decrementing k each iteration. And so what that will look like is, well, we want to keep track of k, and we want to keep track of our root here. And other than that, we just want to return immediately once we see that k is equal to 0. And so to do this preorder traversal, let's do that using a stack again. So while we have our stack or our root, and so let's initialize that as an array. And so typically the blueprint code, once again, we just say, okay, while we have a root, let's keep going left as we can go. And then let's also just add this root to our stack. And then once we have the leftmost thing, let's pop that off our stack, and that will be our current node. So let's do stack.pop. And so from here, we're now basically looking at a node. And so we can kind of decrement k by 1 because, well, we just looked at another smallest element or the next smallest thing. So basically, pop the next smallest node, and this is basically finding the next smallest node here. So now we have it, and so we just say, okay, if k is 0, then we just found the k thing because we did k subtractions, so we would return basically this node. Otherwise, we'll just keep iterating forward using this depth first search manner. Let's try running that. Oh, we want to return an integer. Looks good. And success, so we just want to return the value, not just the node here. All right, so that is, I think, 9 down, or 8 down. We have 3 more to go. So these are the hard ones here. Especially this one I find, construct binary tree from preorder and inorder traversal. So let's go ahead and do this one next. So essentially all that we're given is a tree here, and we want to construct actually we're not given a tree. We're basically given the preorder and inorder traversals, or the values if you traverse a tree in that manner, in order to construct that tree. And so we're given 2 lists of integers, and we're actually building and generating that tree, that binary tree. And so essentially, if you don't know preorder, inorder, or postorder, I'm surprised you got this far. I would say that you should look up the definition of those and make sure you understand, okay, if you're given a binary search tree, how do you traverse an inorder, postorder, and preorder? All right, so this is basically the order in which you would see these nodes, and we basically want to build this tree using these arrays. And so to do that, basically, what preorder is good at is we know that the root is always like at the front. Okay, so we see that 3 is a root, and it's actually at the front. What's cool with inorder is we know that the root is always kind of in the middle here, and everything to the left of it is on its left subtree, and then everything to the right of it is in its right subtree, right? So 15, 20, and 7, that's on the right, and then 9's on the left from this root node. Okay, and so using this information, we can basically always see, okay, well, whenever we build it, we can just say, okay, let's first get 3, and then let's put everything on the left and pop them together. So then we have basically 9 here, and then we have 15, 20, and 7. So that's basically how we use these values here. And then we basically recursively build each of these subtrees. So then we say, okay, what about 9? Well, 9's this. So from here, can we split it? No, we can't. So let's just build 9 and then kind of add that link here. All right, and so then what do we want to evaluate next? We basically look next on our preorder, which is 20. Then we find its index, and then we basically say, okay, what's on the left? 15. So we basically just erase this. We now put a link to 20, and we say, okay, now on the left of 20 is 15, and the left on the right is going to be 7. And so we basically just build out those as well. And then when we iterate next to 15, we then basically split here in the middle, but nothing's on the left and right. Same with 7, nothing's on the left and right, and you're basically done. And so once again, you're basically looking at, okay, we're going to build these trees in the order in which they arrive using preorder. And the way we find out what's on the left and right of it is basically by finding the index at that node and saying, okay, this is on the right and this is on, or this is on the left and this is on the right of it. All right, so if that doesn't make much sense, I think the code really helps for this. And so we'll go ahead and implement it. And so essentially we'll provide this kind of recursive implementation of this. And so what you can imagine here is that we want to return some node. All right, and so if there's no preorder or either of these don't exist, we can't do it. So let's return none. So if neither of these or either of these don't exist, let's return none here. Otherwise, let's actually build this root node. And so the first thing that we want is, okay, we want to find out what's the midpoint for our Inorder, but we also want to find out like what's the next node here. And so to get our new node, we'll just say, okay, let's build a tree node using this class that they've given to us. And we'll provide it basically the next value in our preorder thing. So the first node that we look at is we basically go from left to right, and we're going to look at 3 first. And we build a node using that value. And then we say, okay, where is 3 located? It's located here. And then we basically want to set everything on the left of it in the left subtree of it, and everything on the right in the right subtree of it. And so first we want to find its index. So we just say, okay, let's look at our Inorder array and find the index of this value of our new root. And then from here, all that we want to do is basically update its left and right subtrees. And so this is going to be a recursive call to this method here, right? So same thing here. And so it's going to have to pass these parameters, which is preorder and inorder. So let's call these preorder and inorder. But we're essentially, all that we have to do here is slice them so that we only consider what we need moving forward. And so with the next call, we don't want to use 3 again. We only want to use these values next. And so for preorder, we basically want to say, okay, let's slice from 1 onwards and up to basically the mid plus 1. Because we still want to use the midpoint, but we don't want to use anything beyond that because we've already used it. And so with this, we basically want to say, okay, for Inorder, on the left subtree, that's going to be everything up to this midpoint. So that's going to be colon, everything up to this midpoint. And so what about the right side of the subtree? And so what this looks like is going to be, okay, we want to do everything right of that midpoint. So midpoint plus 1, colon, and then same thing here. midpoint plus 1, colon. Oh, tree node, what's wrong here? So preorder at that. Do I need index out of range? If not preorder, oh, we want to return none. I didn't say return here. Looks good, and success. So that's another one here. So let's go ahead and implement the last two here. So this is binary tree maximum path sum. It's a hard level problem here. And so essentially we're just given a tree here, and we want to say, okay, what's the maximum path that we can traverse? And so the clever thing with this is it doesn't really have to technically start at the root. It just has to go basically from some node to another one. So for this case, you basically want to go from 2 all the way to 3, like so. And then for this one, you basically want to go from 9. You don't actually want to do this. So if you start at 9, this is actually negative results. And so you might as well start like at 15 here instead. And so you don't go down this path. One thing to note is say, okay, what if we had like 10, this was positive 10, and then this was 10, and say this was 10. And so what you want to understand here is that you want to go down this path. And so you see that if you go down this path, you're going to get 40. But what you can't do is then say, okay, what if I also want to go down this path as well? Unfortunately, that's not valid. And so you can only choose one of these decisions here. And so if you went down that path instead, you'd actually get 37, which isn't as big as 40. And so you want to go down this path instead here. All right, so to implement this, essentially we're going to do this recursively, and we're always going to maintain like what is the maximum I guess path as we're propagating along here. But there's a certain point where we want to decide, okay, well, which of these paths do we want? Do we want the left or the right path? And so essentially we're going to have to maintain like what are these total sums that we're getting going down these two individual paths, and we would have to make our decision there. And so we just also want to maintain what is the maximum sum we've been able to get so far from this point onwards. The only other thing that we also want to keep track of is, okay, if we get like a negative path, we'll basically prune that and just use 0 instead, which is basically saying we'll start here instead of using what happened prior to us. All right, so I think that's pretty much it. I think we'll go ahead with the implementation of this, and we'll just see how it goes. So essentially, I think that what we should do first is just say, okay, we'll want to split the logic of essentially iterating through here and then just propagating the results backwards. And so essentially, in order to maintain the maximum, typically it's easier just to use like a global variable. You could use it as another parameter, but in this case, how I implemented it, and I found others, was using a global variable. Sometimes it's a code smell, but I found it was the most intuitive answer, so it was easiest for me to explain. And so we'll keep track of some global variable called max. And so initially, let's just set this as like -infinity. And so we'll want to call a particular method which basically finds this max. So let's define, and we'll basically find the max. And so we'll basically want to call this method here, so find max from this root. And we're just going to return this max kind of sum path here. All right, and so from here, essentially, what we want to do is keep updating this max. And so like we'll want to constantly be comparing this max against something else. And so from here, we just want to say, okay, sum the max. It's basically going to be everything from the current node and all the possible paths we could go from the left and the right. And so what that'll look like is basically the root value plus the left path and the right path. All right, so this is basically allowing us to use every possible path from prior to us. All right, so we're basically saying, okay, everything from this point on, we want to continue to maintain what that current maximum is. All right, and so to get the left and right, it'll be like so. So we want to have our left. We also want to have our right here. But we want to understand that, okay, well, in order to do this, we want to be able to prune whenever we get a negative path. And so if we're actually getting like a negative path like this, 9 plus 10 is actually -1, we'll just say, okay, let's just use 0 instead of this here. And so let's just say, okay, let's grab the maximum of 0 and this possible path here. All right, and so we'll just basically recursively call this but root dot left. Same thing here, find max, but root dot right. And we just want to use the self keyword here as well. We want to specify that here, and then also here. All right, and so from here, in order for us to essentially choose between, okay, do we want to go down this path or this path? We can't use both. And so to do that, we want to say, okay, and once again, I'm using my example of, okay, what if these were all positive? And so we're going like this, but we had to choose between picking like 0 and 10 here. We want to only choose one, we can't use both. And so essentially, we just want to return whatever the current node is, so root.val, plus the maximum of these two possible paths, left and right. Okay, let's try running that. Oh, invalid syntax. I don't need a colon here. And this is saying none type. Oh, so what about our root here? So if there's no root, we'll want to return null. So if not root, we want to return 0, sorry, I mean. Let's think. Oh, I have to say return. Looks good. And success. So I think this one's not super intuitive. I think the idea of pruning, of saying, okay, if we have a negative path so far, we'll just use 0 instead. But then also, okay, we have to choose at each point whether we want to keep track of the left or the right path from here. And essentially from this point on, we're just maintaining what's the maximum results we got from both of these left and right subtrees. All right, so I think that's good. We'll go ahead and implement the final one here called serialize and deserialize binary tree. All right, so this is a lot of comments here, so I'm just going to delete these. But essentially, all that we want to do is we're given this tree here, and we essentially want to, when we deserialize, or when we serialize it, we want to say like, okay, we have like 1, 2, like none, and so forth. I think I'll undo this. Do they have a good example of it? I guess not. And so essentially what we're saying is that we want to traverse this first in like preorder traversal. And so whenever we see a null, we're essentially converting it as a string as like n. And whenever we see an actual node, we'll basically be appending a value like 1 or so forth. All right, and so essentially what this would look like would be like something like 1, and then 2, and then basically it has nulls at the end of it. And then it has like 3 and so forth. All right, and so that's how you serialize it. When you deserialize it, essentially we're converting that string that we just made using preorder traversal to then be, once again, its proper tree like form, if that makes sense. All right, and so essentially all that we want to do is say, okay, if our root is like none, then basically we have the case where we have n here. Otherwise, we have the case where we want to be concatenating that kind of string here. And so we want to say, okay, let's create a function here called Preorder. And we always have the root. And so if the root is none, we just want to return n, which represents none in this kind of string serialization of the tree. Otherwise here, we just want to return basically the string of this root's value, and then we just want to continue going left and right. And so we just want to call Preorder and just do root.left. I guess this is technically Inorder because we're visiting the current node and then the left and right. So we just keep adding, I guess it's Inorder, root.right. Great. Inorder. Awesome. And so all that we have to call here is basically we want to return, we want to call this method here, so return Inorder on this root. But once again, because this is a string that we're serializing, we want to add commas in between them. And so to do that, we just want to say, okay, well, let's return, I believe it's, yeah, so we don't want to return necessarily a string, but we're going to create it as an array. So it looks like this, so like 1, and then like n, and so forth. And so we're basically going to have these delimiters here. And so we just want to say, okay, let's go ahead and we have this, but then let's split it using commas here. I believe that makes sense. Because when we do a split by it, I think what we'll have this return is actually an array, and then we'll concatenate it using like this delimiter. And that way, so when we have that string, we can then convert it back into an array using that delimiter. Okay. And so what we'll say is, okay, so we have this array here. And so we're instead going to want to also be appending this array here. And so how do we convert that array into a string? We just want to say, given this array here, let's join it using this delimiter. I believe that this comes after the delimiter that we're using, like so. Great, and so essentially this is returning a string with the delimiter comma, and we're representing the nulls with n, and then the values as like the string value equivalent. And so from here, we want to say, okay, how do we get our values? Well, that's going to be the data that we're given, and we're splitting by this delimiter. And so we want to build our tree. And so naturally, we're going to want to return like some root here, some new node. And so we want to construct our node using the particular value that we're looking at. And so we're essentially going to have to maintain the same thing where we're using depth first search. We want to keep track of, okay, this is basically our data. So it goes like 1, 2, n, 3, 4, etc. And so we'll initially have an index that's pointing here. We're going to propagate it from left to right here as we evaluate them, like in preorder. But essentially, after we split this data, we're dealing with an array. And so we also want to be constructing these tree nodes as we kind of iterate through here. So we'll define like some index here. So I, which initially is 0. And so we'll want to say, okay, let's define this kind of depth first search method where we have our current root that we're looking at. And so from here, we essentially want to create our tree node. I guess not from the root, but from whatever value this index is pointing at. And so we'll just want to use our vals at this particular index here. And so that is a string, so we want to convert that into an integer. And so with this, then okay, how do we go from left to right? Well, we just visited a node, and so want to increment, basically I is being incremented by 1 here, and then its left will have to be updated. And so I believe root.left we'll basically just have to call this here, and then same thing with root.right. Let's try running that. Oh, I think I just missed a colon here. So we're going to want to call this depth first search method. I is not defined. We want to use self. Let's see, invalid literal. So how do we convert that into it here? Do we not need that? Index out of range. So I plus equals 1. Oh. So if it's n, we want to return null in this case. Otherwise, we actually want to get the value. And so we just want to say, okay, if that particular node is that, so if vals at I is this, then let's just move our pointer forward. And so we just say, okay, this is being moved forward. Otherwise, we're actually going to be moving it like so, but we always want to be returning some root here. So initially it's going to be nothing. And so if we hit null, we're going to return null here. But if it's not null, we're actually dealing with values that we can work with. And so we'll want to be incrementing them. This also gets incremented here. That looks good. Let's try running that. Looks good. And success, that's the last one. So once again, just to iterate through this, essentially what we did here was we wanted to serialize our tree into like the string equivalents, and we're essentially just returning I guess it's a string here, but then it's being concatenated using these delimiters here. So we have 1, and then we have like 2, then we'll have like null, maybe null again, and then 3, and so forth. And so this is a string. But then when we do vals.split, we split by this delimiter to then get the array equivalent of it. But these are all strings still, like so. And so whenever we see that what we're looking at is null, we just return like null as that node. But whenever we see that it's an actual value, we want to create that tree node using that kind of integer equivalent of that string. We naturally want to, with each iteration, be incrementing to the next point, and we just set the left and right node, calling this function recursively. All right, so that is the final one. That's all 11 questions. So I hope this helped a little bit. Feel free to like and subscribe if you want to keep watching. I'm going to be doing the rest of these. I think the main takeaways here is that you really want to understand how to implement depth first search as well as breadth first search, just knowing essentially what is the blueprint code both recursively and iteratively for implementing these. And then within depth first search, you want to know how to implement basically preorder, post order, and Inorder, right? And so what is the order in which you want to visit these nodes in this kind of depth first search manner? Other than that, I think that's pretty much it. I think that knowing a lot of these, you'll reapply them. Like we use this is same tree, I believe, multiple times. Like typically like something like finding the lowest common ancestor, that's like a whole, there's probably like 20 plus problems on LeetCode using this possible pattern. And so I think this is a great foundation for working with trees. And I think just working both like recursively and understanding how to implement that into like an iterative code is really helpful for dynamic programming. But really just understanding how to work with recursion is just really useful for a lot of these problems. Like graphs use recursion, backtracking, same thing with a lot of the stack stuff, because stack is technically an iterative way of recursion. So anything you can do with stack, you can do with recursion. And yeah, so just a lot of these problems inherently use recursion within it. So it's great working with trees, just understanding the relations and how to convert that recursive relationship to using stacks and queues. All right, so feel free to like and subscribe, and just leave a few comments and just let me know, what you want to see next or some problems that you're having challenges with. So thanks again, and good luck with the rest of your algorithms. See you later.